So hello, welcome everybody to the course Foundations of Language Technology, TU Darmstadt, winter semester 2020. This is lecture 13, and this time we're gonna speak about a little bit about semantics. So as usual, what you can do to prepare for this week, go back to the last week, recapitulate the basic concepts and the definitions, check the tutorial. What you can also do is this lecture is not based on the NLTK course book, but rather what we're going to introduce very briefly FrameNet. Here's a link to FrameNet. There's also an NLTK API to FrameNet, which you can check out here. And finally, the second part of this brief lecture will be about how to use deep learning for semantics. And if you want to have an additional reference, go check the corresponding deep learning lecture in the FOLD course. So as usual, we do a small review of what we have seen in the last lecture. So we have seen syntax and grammar. And in terms of syntax, we have seen two syntax formalism. The first one was constituent grammar. And in particular, where we have those different constituents, such as noun phrases, verb phrases, and similar phrases, also preposition phrases, adjective phrases, adverbial phrases, etc. And one instance of constituent structure is context-free grammar, and we have seen how context-free grammars look like. Basically, they have those rewrite rules. Left-hand side can be rewritten into some symbols on the right-hand side. And we've also seen probabilistic context-free grammars. The second formalism that we have seen was dependency grammar, where instead of having those rewrite rules, we have like relationships between words, and this is a directed relationship between words. So one word is the head and the other one is the dependent, and basically those relationships form a graph, as illustrated here, where the nodes are the words and the relationships between the words constitute the relations in the graph, and in particular they form a tree. So it's a special graph. So in this lecture, we are at the top of the pyramid in NLP. We're doing semantic analysis, where semantic analysis is like understanding the meaning of text, and this is apparently one of the end goals of natural language processing, having an understanding of the meaning of text in a computerized form. So let's start out with looking at some interrelationship between syntax and semantics. When we have a sentence, such as the window broke or the man laughed, as we've seen in last lecture, we can derive a syntactic analysis of the sentence in form of, let's say, a context-free grammar. So we would get such a tree which says the sentence consists of a noun phrase and a verb phrase. And okay, we have such an analysis. At the same time, we can also have a semantic analysis by identifying the semantic arguments of the verb of a sentence. So in both in syntax and in semantics, one typically thinks that the verb is the most important part of a sentence. So we start out with the verb and identify its arguments. So the verb laughed takes one argument, and this is a subject, for example. So somebody laughed or somebody is laughing. And then what we see when we compare those two things is that we have a certain similarity here, because the noun phrases are the arguments of the verb here. So it's really the noun phrase which are the argument of the verb phrase or of the verb here. Right, and this would even hold for more complex sentences, such as Tony broke the window or Tony became a banker. In both of those cases, again, we have a verb, and it has two arguments in both cases. In one case, it's Tony, and the window as the two arguments. In the other case, it's Tony and a banker, which are the two arguments. And then again, we can then again we see that those arguments are phrases, noun phrases in both of those cases. Now, those noun phrases, they also take a certain role, right? So intuitively, the role here of Tony is the agent, because he is doing something, right? He is actively doing something, so we could call him an agent. And he's doing something to something, and the thing that upon which he is exerting his influence too is the window. So he's doing something with the window. So intuitively, the window is the patient. So the window is the recipient, right? So something is happening with the window. And this is a kind of semantic interpretation where we have a predicate and a verb that has two arguments, and those arguments have different semantic roles. In the last example here, we also see that even though the syntactic structure is the same as the previous one, the semantic roles might change. So even Tony may be the patient even though he's in the first position, and the last verbal phrase doesn't always have to be in the patient role, it can also be in the result role. And we can do the same for more complex sentences, such as Tony broke the window with the hammer. Again, we have a noun phrase, a verb, another noun phrase, and a prepositional phrase. And to each of those phrases, we can assign some semantic role. And when we talk about semantic roles, we're in the field that is called, in natural language processing, Semantic Row Labeling, SRL, which is exactly the task of identifying the semantic arguments of a predicate is a verb, and assigning those arguments their semantic roles. So in short, Semantic Row Labeling answers the question, who does what, to whom, when, and where. And there are different formalisms for semantic row labeling. Whenever we have a linguistic theory, there are multiple different variations and interpretations and realizations of that theory, and the same goes with semantic row labeling. So in one theory, for example, WordNet semantic row labeling, we have those agent, patient, beneficiary roles, as we've seen before. In another theory, we just simply call those, and this is like a computational theory, it's not a prop bank is like a computational implementation of a theory. Those arguments may have role names of the form arg0, arg1, arg2, and arg3. And when we go to another framework such as FrameNet, the roles, the semantic roles, may have names in this particular example sentence of seller, goods, and buyer. Okay, so we have different formalisms that differ in the kinds of arguments that they recognize, and maybe also in the interpretation and names of these arguments, but still all those theories are to a large degree similar or even identical. So when we focus very briefly on one of those theories, it would be the theory of semantic frames, which goes back to Fillmore 1973. So this is a little bit a more complicated semantic theory, which holds that a semantic frame is a prototypical situation, such as like a prototypical situation typically involves something with a verb, such as buying or selling, which could be a financial transaction. That could be a prototypical in the real world, that we have a financial transaction. And this prototypical situation involves participants or props. Participants are animate entities, props are inanimate entities. And those participants or props have different semantic roles. So the participants could be like Tony, the props could be the hammer and the window, and the prototypical situation could be that of breaking something, or destroying something. That could be the prototypical situation, as in the sentence Tony breaks the window, where then we have the predicate with its arguments and their semantic roles. So there's also a lexical resource, or like an NLP resource for FrameNet for this semantic frame concept, and this resource is called FrameNet, and it contains about 1,000 frames, so about 1,000 prototypical situations, along with their participants and props, etc. So I will not go more into the detail of FrameNet, but let me just quickly outline how we could use this semantic row labeling for doing actual NLP tasks such as question answering. So in question answering, we have a question that is input by a user. For example, we have a text corpus, and what the computer is supposed to be doing, it's supposed to be answering the question from the corpus. So, and what are we going to do? How are we going to use semantic row labeling for this? Well, we would take our input corpus, our input question, and we do the semantic row labeling. And if we're in the context of this FrameNet framework, we would identify the prototypical situation, which, as I said, is usually a verb. So it's bought here. It's the buying word. That would be the prototypical situation, so it's a financial transaction. We would identify its arguments and their roles, their semantic roles. So we would say Chrysler is the goods and Daimler is the seller. So we do this to our question. We do the same thing to our text corpus. So we identify the predicate and the arguments, and then we match up. So we find here goods and goods is here, seller and seller is here, financial transaction and financial transaction here is here. Then the only thing left to do is to find out what is the who referring to. So we would have two further arguments here, one about price and one about the buyer. And once we know that who is asking for the buyer, we can give the answer. So this is a high-level intuition of how we could use semantic row labeling, for example, in the context of FrameNet, to do question answering. So semantic row labeling is a kind of semantic representation of a sentence, right? You have the sentence, and you identify the predicate and the arguments of the predicate, and you give the argument semantic roles. In this way, you have a discrete representation of the sentence, which gives you more information about the meaning of the sentence. What does this sentence actually mean? And it's certainly more complex and more informative than those syntactic analyses that we had that just outlined to us which are the noun phrases, which are the verb phrases. Here we really go deeper because we also identify what semantic role do these noun phrases and verb phrases and adjective and prepositional phrases have. But it's certainly also less complex than doing a full logical representation, as we would know from, let's say, predicate logic or even more involved logic formalisms. So semantic row labeling may have a nice trade-off between complexity. So it's not between complexity and tractability. So it's certainly not shallow. It's more complex than semantics, but not fully complex. And therefore, because it's not fully complex, we can also design efficient algorithms to infer this semantic representation that semantic row labeling is aiming for. There are a couple of example applications that we can use semantic row labeling for in natural language processing. One of them that we have outlined is question answering, but we can certainly use it in other semantic tasks such as word sense disambiguation or machine translation. When we want to do semantic row labeling automatically, and if we want to do it in the context of FrameNet, what people have often done is to take a two-step approach, where in the first step in a given sentence they would identify the frame, so they would identify the verb, and then match this verb and maybe some complements to the verb with FrameNet, so to find out what is the prototypical situation that this verb is referring to. And in the second step, we would identify the arguments, for example, using biotagging, and also by reference to FrameNet. So we check which frame is being invoked, which arguments does it typically have, and then we try to map this back to the actual sentence. And we would also have to label the semantic roles of the arguments. Luckily, we don't have to do this with regular expressions or something, but we can use this with machine learning approaches because annotated corpora with FrameNet frames are available. For example, the FrameNet full text corpus. So we have such corpora annotated with frames and the arguments of the semantic frames and the labels for those arguments. So we can actually train a system on the annotated corpus and then apply this system to novel unseen sentences. And if we want to develop a system and we don't want to base this system on deep learning, for example, but if we want to take the classical approach with features, we could use rich linguistic features to induce a semantic row labeling system, and these features could be based on syntax, for example, because we've already seen that syntax and semantic row labeling go together to a certain degree, so certainly having a syntactic knowledge would be helpful, and this again reinforces our intuition that we have a linguistic pyramid where the higher levels like semantics build on the lower levels such as syntax. Our second approach to semantics, and this second approach is based on the current state of the art, namely deep learning. So we do semantics with so-called embeddings, and embeddings are vector representations of words that are induced by deep neural networks. So recall this from a previous slide where we said for each word we can somehow magically obtain its word vector, its word embedding. And this word embedding is simply a vector representation assigned to each word. So we have all the words of our lexicon and we assign with each word a different vector. Now, in reality, those vectors are usually of length or of size, let's say 300. In our toy example here, the size is exactly 1, 2, 3, 4, 5, 6, 7. So in this toy example, they are 7-dimensional. So basically what this means is that we have all our words in a 7-dimensional space or in a 300-dimensional space. Now, we cannot visualize a 7-dimensional or 300-dimensional space. So what we can do instead is we project the 7 or 300-dimensional space down to 2 dimensions, and then we can visualize our words via their vectors. And then what we would see in this example, in our example case here, could be that intuitively similar words such as cat and kitten are close to each other, and they are further apart from a word that is intuitively more dissimilar, such as dog, and even more dissimilar from other random nouns, such as the word houses. So then a couple of central questions arise in the context of those vector representations, which also go by the name of embeddings. So how do we actually know that those vectors capture semantics? Semantics is the field of meaning. So how do we know that our vectors capture the meaning of words? Well, first of all, that's an empirical question, and we can just test it out. So as I've shown in the previous example, we can just visualize our words and then check out whether that is intuitively what we understand by semantics. But we can also know a little bit when we look at the training process of those word vectors. And those word vectors are trained in such a way that, so for each word we want to induce a word vector, such that from this word vector then we can predict the context of the word. So, or rather, yeah, so that we can predict the context of the word. So, and there is a famous principle in linguistics which says you shall know a word by the company it keeps. So once you know the word that are in the neighborhood of any given word, you also know the meaning of this word, right? And by this principle, and this training process is exactly realizing this principle, because it tries to predict the neighborhood from each of the word vectors. So if two words are intuitively similar, they also have the same neighborhoods, and therefore they will receive similar vector representations. So this is a justification of why the word vectors should actually contain semantics, and then we can verify this this intuition empirically by, let's say, visualizing those vector spaces. So our second central question is, once we have those vectors, how do we actually compare the semantic similarity of two words? How do we know whether two words are semantically similar using those word vectors? And this is very easy to answer. Once we have the words, we take their vectors, and then we compare the vectors. So there are many ways of comparing vectors, which you probably know from school or from other courses at university. One is like the Euclidean distance between two vectors. Another one is what is called the cosine similarity, which measures the angle between two vectors. And the smaller the angle, the more similar are the vectors, and the bigger the angle, the more dissimilar are the vectors. And by analogy or by extension, the more dissimilar are the two words under investigation semantically. And our third central question is, how do we actually evaluate the quality of our word vectors? So you can assume that there are different word vectors out there, so different approaches, different. So I said that those word vectors are obtained from deep neural networks. So deep neural networks have hyperparameters and initializations, etc., etc. So you can get slightly different word vectors from different parameterizations of your networks. So how do we know which one of them are good? So one answer is we can take a human benchmark, such as the word similarity 353, and then compare the human benchmark to the prediction given by our word vectors. So how does word similarity 353 look like? Well, it has two words such as plane car, train car, telephone, communication, and then humans have given score that measure the similarity between those two words. And humans would typically give numbers, let's say, from 1 to 10, and then we take 100 humans and we average them so that we get numbers such as 5.77. Good, so we actually have those numbers. Now we can take our word vectors, assign each word the word vector, compute the cosine similarity, then we get another array of numbers. Then we can compare those two arrays, for example, using the Spearman correlation coefficient, and then we know how good the quality of our specific word vector space is. Good. Another important aspect is actually we are not so much interested in vector representations of words from a linguistic point of view, because intuitively, when we're doing natural language processing or linguistics, we're interested in larger objects, such as the meaning of whole sentences. So we would actually want to know how similar is the sentence "lion is the king of the jungle" to "the tiger hunts in the forest" or to "everybody loves New York," right? So this is actually from a higher linguistic viewpoint what we're interested in, and also from an application point of view. So then we have to induce sentence embeddings. So this is vector representations for whole sentences, and there are multitudes of ways to do so. One of the simplest ways to do so is we just take the average word embedding. So we would take the embedding of each word in the sentence, and we average this, and then we get the average word embedding as a sentence embedding. So that's a simple baseline. There are more sophisticated approaches, and if I want to use an easy-to-use software, use SentenceBird available here. So this is very easy to use and gives high-quality sentence representations. Good, and Then once we have sentence representation, we are faced with the same questions, namely how do we evaluate the quality of our sentence embeddings once we have some techniques such as average or sentence bird. How do we measure how good it actually is? We again would use a human benchmark for comparison, such as the STS benchmark, where STS stands for Semantic Textual Similarity. And here there are two sentences rather than two words, such as a girl is styling her hair, a girl is brushing her hair, and then again we have a human similarity, which is the result of the average of many human semantic similarity scores between any of those two sentences. And then again, as before, we would compute the cosine similarity of the embeddings that result from any particular sentence embedding technique, such as average or sentence bird, and then compare those similarity scores to the ones that humans have given to measure the quality of our sentence embedding technique. So as a take-home message, we have seen two approaches to semantics. The one was based on semantic row labeling, where we identify the arguments of predicates and assign semantic roles to them. This definitely is a form of semantic interpretation of a sentence. And arguably it yields a good but maybe in a sense shallow understanding of a sentence, but still better than, let's say, a syntactic, a purely syntactic representation of the sentence. Secondly, we have seen semantics from embeddings, which are word vector representations available for words and sentences. We have seen that arguably similar words and sentences should have similar representations, and arguably they also have similar representations, both by introspection of the training process and as an empirical finding. And as a third point, in the context of those embeddings, I want to mention that they are arguably easier to use in applications than those semantic row labeling representations that we would get, because semantic row labeling is a discrete operation, so we have annotated our sentence with discrete labels, whereas those vectors are really easier to work with. It's very easy to multiply, add, or subtract vectors, or to do some mathematical operations, but with discrete annotations it's harder to work with in NLP application scenarios.